So we're going to talk about Apl64 character data, and there's a number of new types that have been added to the system, primarily to support Unicode characters, but also to give an alternate character representation, a new string data type. We'll get into that. So in just to contrast differences between that, in APL plus Win, we have well, let's just go down through the table. So we have a compact character representation, 1 byte per character, and that's traditional classic APL plus Win and previous APL pluses character representation type. Internally, I don't know that it's ever in the documentation this way, but internally we've always referred to this character representation as Z codes. And they are the 1 byte representation of things, and they don't correspond with, they are unique to APL. They are basically your standard 1 byte ASCII mappings of character positions, but overlaid with APL characters that don't exist in the ASCII character set. And so these things like reshape and take and drop, iota, are all non-standard characters, but they're in the Z code, they're mapped into specific positions within quad AV, and that has worked for the most part well in APL plus Win. We have the exact same thing in Apl64 and APL plus Win. In the documentation, I don't know how much it is distinguished between these, but I tend to refer to these as compact characters or Z code characters, and that's your standard ones. We've introduced a new Unicode character, which is a 2 byte wide per character, and that can represent any Unicode character that exists. Now, it's actually what's called a UTF-16 representation, which uses the Unicode actually is a 21-bit wide character representation, but the Unicode 2 byte character only has 16 bits of data in it. So there's a little bit of a dilemma of how do you represent that, and I'll get into that in a minute. But basically, there is a mechanism by which, even using just these 2 byte characters, we can represent all the Unicode characters. We have a new data type called string, which is distinct from, similar to, but distinct in a number of ways from a standard APL character array, whether that is a compact or Unicode character array. You classic using single quotes or double quotes to delimit the bounds of the character array. And then we have strings, which uses a different notation for the start and end of the string. And that's a new type. It's also Unicode in nature. It's 2 bytes per character. And we have quad UCS characters. These are actually 4 bytes per character, and it's the same in APL plus and APL plus Win and Apl64. We won't go into much detail on quad UCS characters today, so I just refer you to the documentation for that, except that unlike in APL plus Win, where UCS characters, if you tried to print out a variable that had a UCS character value, it would just print out something like 3 less than symbols, UCS character or UCS characters, and then 3 greater than symbols, and it wouldn't show you the text. In Apl64, we do display the actual Unicode characters if they're displayable. And if not, we'll put some kind of a blot that shows that we don't know what that character encoding represents, but it displays just like regular character data, but with a broader range of possible things. So aside from UCS, so let's kind of like for the moment kind of push quad UCS to the side, because it's kind of a weird and specialized type. It doesn't participate in all APL operations. It's not a full-fledged thing, but it's useful for some certain purposes. But let's push that aside here and just look at the regular character data. And for that, really, APL plus Win had 1 displayable data width, which was the 1 byte character encoding. And Apl64 has two widths, the 1-byte Z code and the 2-byte Unicode, plus the new string data type, which is a 2-byte Unicode. And all the types except for quad UCS display as Unicode characters in the session history. So any output that's generated is displayed properly. Okay. So this, nobody needs to see this, but just to be complete, I put this in here. Character data entered in Apl+Win is entered inside of either single or double quotes. So as the example shows, we can have a single quoted character vector, or using double quotes, we can do that. And a single character inside of these quotes is a scalar value. In other words, a scalar which has a rank of 0. Any other number of characters, be it 0 or greater than 1, is a vector. So as you can see in the code at the bottom of the screen, S is assigned quote X quote, and V is assigned quote ABC, and the shape of S is empty, and the rank of S is 0. So that's a scalar. And the shape of V is 3, and the rank of V is 1. So that's a vector. Okay, and entering character data here, we can embed quotes inside of character arrays by two different ways, either using the other style of quotes. So if I've got this string, like on the first line, the variable don't, and I'm using double quotes to delimit the string, and I can use a single quote inside of that to represent a single quote in the string. Or in the second line where I've got embedded, I'm saying in single quotes, I make the outer bounds of the string, of the character vector, but I use double quotes inside of that string. So if you use the opposite quote, that's all fine and good. Or as you all know, I can also double up the delimiter character, the outer delimiter character. So I can say quote, please DON quote quote T quote, and the doubling of the character represents a single occurrence of that. So as you can see here, and we can do the same with the opposite set, with the other delimiter, the double quote character. So this is all completely standard, and I'm sure you're all intimately familiar with that. Okay. So all of this works exactly the same in Apl64 as it did in Apl+Win. However, in Apl64, we don't have in Apl+Win, we had a restriction that there were 256 possible character values. These are the 256 elements of quad AV, and these are the Z code character set. But in Apl64, you can enter any Unicode character directly into the string. So in this case, I'm saying hello in English, which is hello, and then in Chinese, and then in Japanese, and then in Russian. And those characters, even though they don't exist, those Chinese, Japanese, and Russian characters do not exist in quad AV. They are part of Unicode, and we can paste them or type them, if you have an appropriate keyboard, directly into a string. And any kind of emojis or any kinds of things like that you can copy from a website easily, you can paste those directly into a string as well, and that all works just fine. It's just standard Unicode character handling. So when you enter a string in quotes, single or double quotes, Apl64 automatically chooses the most compact representation for that data. So if all the characters are elements of quad AV, it will represent that data in the compact 1-byte character set, the Z code character set. Otherwise, it uses the 2-byte Unicode characters. And you can differentiate between the type of string you've got by taking and looking at the monadic quad Dr of the data. And it will return an 82 if it is standard traditional Apl single byte character, and it will return 162 if it is Unicode characters, a 2-byte array representation. I don't want to go in deep into quad Dr, but the way monadic quad Dr queries a data type is the last digit is a a type that is unique to each fundamental data type that we support. So Boolean data has a 1 as the last digit, and the digits, the digits in the tens and hundreds column are the number of bits of width of the data. So 82 is an 8-bit character data type. The 2 represents this is character data, and the 8 represents it's 8 bits wide. Whereas a 162, the 16 is the number of bits, so 16 bits or 2 bytes of width. And the 2 again says character. So 82 and 162, the 2 means these are both character data type, and the 8 and the 6 differentiate between their data widths. And so there's an example here where I create the English alphabet, and the Russian alphabet. And then I look at the quad dr of the English variable, which is 82, and of the Russian variable, which is 162. And I look at which characters of English are elements of quad AV, and they're all elements of quad AV. And I look at the Russian string, the Russian character array, and I ask which of those elements, and none of those are elements of quad AV because none of the Russian characters are elements of quad AV. So therefore, we can see that, which is good. Now, if you search for a non-standard Unicode character, so by non-standard I'm saying a Russian character or something like that, and you do quad AV iota to search for the index of that, it's always going to return 157 if you're in quad IO, assuming you're in quad IO 1, and it would be 256 if you were in quad IO 0, because these, and it returns that because you're past the end of quad AV. These characters are not part of quad AV. But you can use quad UCS monadically to get it's kind of analogous to using quad AV iota, little different. You'll see that in a second, but you can use that to get the Unicode index, or the code point index of any character that you send. So as you can see on line 60 and 62, where I'm using quad AV iota, I get all of the English characters showing me their index in quad AV, and all of the Russian characters are returning 257 because they're not elements there. But if I apply with English, I look at quad UCS of the English characters, we get the same indexes as we got with quad AV. And then my phone is dinging like crazy. I'm gonna turn the ringer off. Okay, then if you then look at the Russian characters, however, you see you get a very different set of indices, because these are the Russian character plane that these are in, and we get those indexes, those Unicode indexes back. And if I catenate two arrays together, character arrays together, we have a mixture of types, but the ones that were part of quad AV, the English characters, we see their indexes properly, and the ones that are not, we see their Unicode indexes. Okay. We'll come back, lots of questions, any questions you all may have, we'll circle back around at the end of this and do that. So let's talk just a little bit about quad AV indexes versus quad UCS indexes. Quad AV indexes work as usual for standard characters, but UCN, the return value, if you apply certain characters that you think of as standard characters that are part of quad AV, and you use quad UCS to query their indexes, like in the second block of code, I'm using them to look at the values iota, row, and take. Those characters are different indexes than quad AV would give you, and that's because quad AV encodes characters that are not part of the ASCII character set using code positions that are part of quad AV. These are not the standard positions, and if you took those characters and you represented them in any other language or in a document, for example, and you use the indexes that we use in standard APL plus win indices, you'd get the wrong characters, and they would look they wouldn't be what you're expecting for the APL. But if you use the character positions that quad UCS returns, those are the standard UCS characters. So there are Unicode characters for iota, row, and take in a standard position, and those are the positions that we're returning when we use quad UCS. So quad UCS returns Unicode indexes of characters, while quad AV returns the Z code indexes, or returns 127 in origin 1. All right. There's a new string data type, and the string data type, well, let's talk with as we reviewed already. Regular character data issued in the traditional way uses single or double quotes, but in Apl64, we can use the chevron characters that are shown here, either in a single chevron where there's one opening and one closing chevron in the string, or you can use double where there's two at the beginning and two at the end of the string. And so in the example code on line 81 and 82, we're defining a string. And then if we look at its data type, we see for both of them that we've got a string type. And this is type 4, the last digit of the quad DR. And the 16 is how many bits wide the data is. So 16 means it's 16 bits or 2 bytes wide, Unicode width. And the type is 4, as opposed to 2, which is what your standard character array has. So whereas a Unicode string, a character vector containing Unicode characters would have a type of 162, but the string, which is a little bit different, has a type of 164. You can type these characters. The opening chevron, the left chevron, if you will, is an Alt Shift and then the less than symbol. And the other one is an Alt Shift and then the greater than symbol. So you can directly type the opening and closing chevrons. These are more formally called, and the people pronounce this in different ways. Some people call it something like guillemets, and other people call it guillemets. But I just tend to call them chevrons, and most of us around the APL shop there, where all of the developers tend to refer to them as chevrons or chevron strings. Okay. And so what are some of the differences here? There are some substantial differences. We did talk about the quad DRs of the compact and the Unicode and the string types, and so we can see that demonstrated here with the three different kinds of character data on line 91, 92, and 3, where we're creating regular compact characters assigned to E for English and R for Russian and S for string. We've got those three types, and we query their quad DR, and we see an 82, a 162, or a 164. Important distinction is the 2 or the 4 at the end of that, at the last digit of the data type, to tell us if we're dealing with standard character array or a character string. So some other differences are the regular character arrays have a shape that depends on the number of characters in the array, but a string is always a scalar, no matter how many characters are enclosed in the string. So what we can see here on line 109, 111, and 113, if we look at the shape of a single quote, that's a scalar, and so we get back the shape is an empty value. If we did the rank, it would read as 0, so 2 rows in front of it would return a 0. The quote ABC quote is a 3-element character vector, and the quote ABCDEF is a 6-element character vector. But on lines 115, 117, and 119, we look at the shape of chevron string A or ABC or ABCDEF, and the shape is always a scalar, no matter how many characters are enclosed in it. And what's going on here? Why does this make sense? Well, the way it makes sense as we develop this is that a string is always is a scalar because it's a new primitive data type. If you think about the way a number works, so a number like 1 or 1, 2, 3 or 1, 2, 3, 4, 5, 6 is a single number is a scalar numeric value, no matter how many digits are in it. So a string is kind of, you can think of it as the same way. It's a single, always a single element in an array. It is treated as a unit. And this is actually, and I can talk just a little bit about why we made these choices. But the string, though, is always, like a number, is a primitive entity in the system. And just as you wouldn't want a 1, 2, 3, 4, 5, 6, that numeric value to be a 6-element numeric vector. It's a single number, and you treat it as such. And you think of the strings in a similar way. There's ways to enclose and sort of, or n string and dstring, these we call them, that you can convert them from a regular character array to a string, or from a string to a character array. And then when they're in the array form, you can treat them exactly like normal stuff. Let me talk for a minute, and it's not written on the slides, but why did we choose this? Why was the string important? Well, one of our goals, we have many goals in developing this project, but one of the goals was that we want to be able to, and we're not there yet, but we wanted to be able to more seamlessly interact with other programming languages and other paradigms here. And so there is a big distinction between an array of, like, if we were at some point at a later point, we may be able to directly call C# methods and that are external to APL, that we could import a library and be able to create instances of objects and then call the methods and pass arguments to it. Well, when we pass an argument, there is a fundamental and big distinction between an array in these other languages, between an array of characters and a string. A string is a fundamental data type in most modern programming languages, and it is fundamentally different than an array of character values. And that's really the reason that the string was invented, as not just using the chevrons wasn't just a third way of representing a character array, but instead represents a new data type. And that data type, it has a semantic fidelity that is consistent with the strings of other programming languages that we might want to be able to more directly interact with. And so we, as a primitive type, wanted to have the string be unique and different from our traditional character arrays. And that really is the motivation and why. It's a little bit confusing, but there are facilities for interoperating with this. So the conversion between string and character, the monadic primitive functions, the less than and greater than, can be applied to an array or to a string to convert character arrays to strings, and vice versa, strings to character arrays. So if you take a look at line 133 in the middle of the page, we sign C as quote ABC quote, and we look at its data type, and then we apply on line 136, we apply the less than symbol in front of it. This is called an N string, we call it, and this converts the character array to a string. So you can see the quad DR changes from 82 to 164. Similarly, on line 138, or conversely, perhaps I should say, on line 138, we create a string ABC, and we look at its data type, which is 164, and then we dstring it, which is converting it from a string to a character vector. And so its type, and the dstring type, the character vector type, is 162. Note that the dstring, or the greater than, monadic greater than symbol, converts a string to a Unicode character array That is a 2-byte wide characters, type quad DR type 162. It does not try to demote it to the compact form. The compact form is only demoted to if you directly quote it. So if you're writing code and you say quote and then some number of characters and then an ending quote, we will use the most compact representation. So if all the characters are in quad AV sequence, we will use the traditional compact character representation. If any of the characters are outside of that, so if you embedded in some emoji or you embedded in some characters that are outside of the standard APL character set, we would use the wider character array representation for regular arrays. If you put them inside of the chevrons, they're always Unicode, and there is no demotion to a lowest or more compact data type. So, as I mentioned, the monadic less than primitive function is called nstring because we're going to a string, and we have the monadic greater than primitive function is called dstring, and we're going from a character array from a character string to a character array in that case. And the thing too, you can apply this to a whole array, a nested array or what have you. Any non-character or non-string elements in the argument are returned unchanged. So as you see on line 147, we're applying this and looking at the quad DR of each element to a nested array that contains a 3-element character vector ABC, a 3-element numeric vector 1, 2, 3, and a 3-character long string DEF. And when we look at the quad DR of each of those, we can see the first one is 82, which is a standard compact character array. The next one is a integer array, and that's 323, the 3 being the integer data type, and the 32 being 32 bits or 4 bytes per element. And the last one is 164, which is 16-bit wide or 2 bytes of type 4, which is string type. And if we apply the dstring to those elements, it's slightly, what you see is what it will change is it will change the string to a character array. So the type changes on the last element, it changes from a 164 to a 162. On the other hand, if you apply the n string to those same 3 elements, what happens is that the first element, the quote ABC, gets changed to a string, from an 82 to a 164 type. And the other types are already, well, the numeric types are ignored, they just pass through, and the string is already a string, so we don't do anything to it. Just another little note here is that the n string applied to a character matrix or higher rank array will, well, to a matrix, it will just split it into rows, and each row will be put into its own string. In a higher rank, you would have a rank 3 array applied here. You will get a rank 2 array of strings out of it, and the last axis, along the last dimension, it will slice those into strings. So that's what you can see happening at the bottom of the page. In strings, you can use escape characters. So with regular character data, you can embed quad TCNLs, quad TCLFs, or any other kind of control characters like that, as you see there on line 162. So we can do, quote ABC quote, and then catenate a TCNL, and then quote DEF quote, and then catenate a TCLF, and then catenate HIJ. You could do this more directly in a string using escape characters, and there are a number of escape characters defined. 2 of the most commonly used are the /R. Each of these escape characters start with a backslash. So it's a /R for the return character that is represented by TCNL, and the /N, which the terminology is a little confusing. In APL, we use quad TCNL for the /R or for the return character, and the TCLF is actually called a new line character. But in terms of how those are represented in virtually all other programming context, the /r and the /n are return and new line. So the names that we use for our TC variables, quad TCNL and quad TCLF, are a little backwards, but the mapping is as I show between 162 and 166 there. And those are both producing the exact same sequence of characters embedding in there, but one of them is a character array. The value formed by those catenations on line 162 is a character vector that's being formed with those operations that are taking place. And what if you look at that, you can see that there are actually 1, 2, 3, 4, 5 arrays that are catenated together with 4 catenates. So there's 4 catenation operations and the instantiation of 5 array entities. And that's execution time overhead, a little bit, not a lot, but a little bit. In the other case, with the on line 166, that all happens at the time the function is defined, and it's a single string that is formed, and so there is no execution time overhead to the creation of that, none of the catenation overhead of gluing those different pieces together. So this is actually a nice, and it's also a very easy to read, I believe, and compact way of escaping these strings. So we can do that. So you can see that. Now you do end up with a different entity in the two cases. On 162, it's a character array, and on 166, it's a character string instead, or I'll just call it a string. And so the string is formed on that one. Now, if you want it to be an array, you could just put a dstring in front of that line 166, and then you could do that with it. So there are other escape characters that are allowed, and I haven't shown all of them here. But on 132, I'm showing a backslash, 2 consecutive backslashes represent a single backslash. So the backslash is the escape prefix character that says I'm going to give you some other character following this, and it represents something. And so if you wanted to include a backslash in your string, you would have to put 2 backslashes. It's kind of like using double quote, 2 quotes inside of a quoted string to represent a single quote. It's analogous to that. The \t is the representation of a tab. A \0 represents a null character. And there are a couple more that were just recently added to the system. There's a dash V for a vertical tab, I think. There's a slash B for a backspace, and a slash F for a form feed character in the sequence. So those are also some that are possible. If you want to embed guillemets or the chevron characters inside of the string, you have to escape those. So what you can see on line 145 is you can see that we embed this chevron string, but we have to put a backslash in front of the opening chevron and a backslash in front of the closing one. And then there's 3 other forms that are of primary interest, which are a 2-digit, a 2-digit, a 4-digit, and an 8-digit hexadecimal representation of the number. So slash lowercase x is followed by 2 hex digits that represent a numeric value of some kind here. And actually that is the hex 0 Charlie that we see on line 148 is basically the same as a carriage return or a quad TCNL. And so that's another way of embedding it. It's easier to do /r that I'm just showing you. You could enter it in a hexadecimal form. Or you can enter it as a 4-digit hex using a /u, a lowercase u, and that is the code point symbol for a yen. You could also have just, if you have a keyboard capable of typing it, you could have typed the yen directly in there instead of using the escape. And then we have finally, we're using an 8-digit hexadecimal number when we use a capital U for our encoding, and that is the code point for a for a Unicode for the emoji that is the smiley face emoji. And it turns out, by the way, that if you want to, you can look at something like this. So we could do a Google search or any other kind of search you want to do and ask it for the characters you're looking for. So if I'm looking for the Unicodes for various emojis, I could just do a search for those, pull those up, and this is going to show me all of these different emojis. So if I wanted to create this emoji with the, whatever they call it, rolling on the floor laughing, that's, the big smile, tears coming out of its eyes sideways, there is the code for it. And I'm just going to copy that over here, and I'm going to do it like this, except I need to put in front of it a backslash capital U. I have to create an 8-digit hex number, and when I do that, I'll get that symbol. Of course, I could have just pasted the symbol directly if I have it available for pasting. And so the string in the source code, so in your function, it could either be coded like this if you want to use this, or you could embed it directly into the string like that. All right, so let's come back to here. All right. The other way you can do this, and this is a little bit funny, some of these things, these emojis, and we'll get to this right next, but are actually represented by a pair of what are called a surrogate pair of Unicode characters. This is because the strings, and this is pretty much true in all the modern programming languages, certain characters in the Unicode character set are outside of the basic multilingual plane, and we'll talk about that in just a little more detail. And those characters that are basically bigger than could be represented in 2 bytes are used a pair of characters called surrogate characters to represent them. So you can see on line 158, we're using a surrogate pair together, coded as 2 hexadecimal numbers following each other, and that gives us the same exact output as when we used the single character, or when in my code example I pasted in the character directly into the string. So the surrogate pairs, just a little historical note, is that originally, and when I first was exposed to Unicode was way back, I went out to Microsoft to work in what they call their porting lab when they were first developing or releasing Windows NT. And Windows NT they were really pushing the Unicode there. And so that was really the first exposure I had to it. And at that time, Unicode, they did not anticipate that Unicode would ever use more than 2 bytes. They thought they had covered all languages with a 16-bit character set. And so languages like C, C++, C#, Java, JavaScript, Python, etc., introduced their standard strings using 2-byte wide characters. And they thought they had it covered. But as Unicode evolved, more and more characters kept getting added, and then emojis got added, and then lots of other kinds of things. And I think what they were trying to do with the original Unicode was be able to represent all living languages. But as they expanded it, they were more historical or basically often extinct languages or antique languages or whatever you might say, and they couldn't do that. So they expanded Unicode from 16 bits to 21 bits, but now they had a problem because you can't represent 21 bits with a 2-byte character. And so they differentiated between what's called the basic multilingual plane, the BMP, and the supplementary planes, which are to represent the higher characters that can't be represented in the BMP 2-byte plane. And they call those supplemental planes, or some people refer to those as astral characters. And so that's what led to the surrogates. And let's go over here. So surrogate characters, there are actually two ranges of characters within the 2-byte encoding that are used as surrogates, and they're in this range of hexadecimal D800 through DBFF, or from DC00 through DFFF. And so those different surrogates are used to represent the first and second set of 10 bits encoding, and used as a pair, with the high surrogate always coming before the low surrogate by convention. Those pair of contiguous characters can represent things that are outside of the basic multilingual plane in the supplemental / astral planes, and that's how surrogates work. This is how you encode them. So if you have a surrogate, a Unicode code point like 1F600, the algorithm is simply you subtract that first, the hex 10000, and so you can see this subtraction taking place. You're going to see two notations here: 0x and then followed by digits, or U plus. In the Unicode documents, they'll always show this as a U plus followed by 4 or 5 hexadecimal digits. And so you make that subtraction and you get the F600. If you break that into the two parts, the 10-bit segments of it, the high and the low 10 bits of that residual number, what you get after you do the subtraction in step 1, you're going to get 61 and 1536. If you represent those in hex and then you add those to the base value of each of those surrogate ranges, you will get the two surrogate values. And so this is algorithmically how you would go about doing that. But it's generally far easier to just use the 8-bit hexadecimal code, the U followed by the 8 bits. In retrospect, if I was to do this over again, I wouldn't have the 8-bit code. I would probably have a 5 digits of hex code, but that's not how I did it. And it's been in the code now for several years. So this is what you use to use an 8, even though those, in general, those top 3 digits are always going to be 0, but that's what it is. And so what you can see here, and it's interesting, if you look down on line, you can see on line 172, it's a string that we're created, and we display it and we see the emoji. The next on line 174, we do a dstring on that, and now that's a character array, and we see the exact same output. But if you look at line 176, we're looking at the shape of that, and this is the part to watch out for. In that particular case, you see that the shape is 2. There are 2 characters in that string. It's not a single character, it's a surrogate pair. So there are 2 characters there to represent that single Unicode code point. And that's a little bit tricky, perhaps. If you look at it on the right-hand side, where I've got line 188 and 288, 290, and 292, and we do similar things, you see that that is a single character that's represented in that case. Okay, so let's take a look, and we're getting toward the end here. A couple of structural functions like catenate, reshape, and rotate or reverse. That may be a little bit surprising when you first see them applied to strings versus character arrays. So we're all accustomed to working with character arrays. If I catenate 2 character arrays, I get a bigger character array with all the characters in it. So the shape of the catenation of ABC and DEF is a 6-element vector that, as we see by taking its shape. But if we catenate ABC, the strings ABC and DEF, it's like catenating 2 numbers. If I catenated 1, 2, 3, catenate 4, 5, 6, I would have a 2-element vector containing 1, 2, 3, and 4, 5, 6. The same thing is happening on line 301. I've got a string ABC and another string DEF. I'm catenating those together, and that does not produce ABC DEF. It produces ABC and DEF, just as if you were working in the same way that working catenation of numbers would be those 2 distinct numbers. They wouldn't get merged together. Catenating 1, 2, 3, and 4, 5, 6 doesn't give you 1, 2, 3, 4, 5, 6. It gives you 1, 2, 3, and 4, 5, 6. And so the same kind of thing is happening with the strings. And if we look at the shape of that, we see it's 2 and not 6 because we didn't actually concatenate those together. Now you can join those together. If you dstring them and turn them into character arrays, it all works. Normal character concatenation works for that. If you look at reshape here in the middle column on line 306, we're doing a 2x2 reshape of quote A, B, C, D, E, F, and we get a matrix out of that, A, B, C, D, E, F. If we do a 2x2 reshape of the string A, B, C, D, E, F, we get a 2x2 matrix, except the elements are not A, B, C, and D. They're A, B, C, D, A, B, C, D, A, B, C, D, and A, B, C, D, as you see on line 310 and 311. And rotate similarly. If I rotate a character array A, B, C, D, the output of that is DCBA. If I rotate a string, I get the same string out. And if I rotate the dstring of that string, I've turned it now into a character array, and then the reverse does operate on it as you would expect. Okay, really in the home stretch now. And a string can span, unlike a character array, a string can actually span across multiple lines. But to do that, we have a special symbol, an ampersand continuation character as the last character of the line. So if you look at the function foo at the top of the screen, you can see we start a string on line 1. We use an ampersand on the end of line 1 and then continue that on line 2. So we've got line 1 and then a new line and then line 2. And the output of that, if we executed foo, would be line 1, line 2. There's basically a TCNL or a /R inserted into the string wherever we have a new line in the multi-line string that we have formed. So you can't do this with regular single and regular quoted strings. So but maybe we should support it, and so it isn't supported at this time, however. So you cannot do a continuation and insert new lines into a string for regular quoted strings. So as we see in this example, quote line 1 with an ampersand on the end is a syntax error. We don't recognize the ampersand as a continuation character like we did up here. Okay, but if you're using strings and you want to continue them, you must use an ampersand at the end of the line. So just doing the chevron symbol and then line 1 and then a carriage return as you're editing is going to give you a syntax error there, because it says you have an unclosed string, just as if you had typed a single quote and then some characters and then a new line without typing a closing quote, you would get an error. So that is something you need to remember. If you're trying to make a multi-line string, you need to put an ampersand at the end of every line. There is something else too, that if you have indented lines, like on line 2 here, so you've got a multi-line string, but it's indented, we actually ignore the indentation characters. So what you can see is, though it's got indentation characters here on line 2, there's 4 spaces in front of the line, the output actually ignores those characters. And the editor paints them a little differently. The continuation characters are shown in this blue color by default. They're shown in this blue color. And so on line 2, you see those 4 spaces that are the blue color. Those are being ignored, are not going to form as part of the string. There will be a new line after line 1, but line 2 does not get those spaces as part of its indentation. You can indent things, however. The way you can do this is by using an ampersand at the beginning of a continuation line. So line 2 just has some blank spaces in front of it. Those are going to be ignored, but line 3 has an ampersand at the beginning of the line followed by 3 blank spaces. Those blank spaces are not part of the continuation sequence and will be indented. And similarly with line 4 and 5, you can see, and if you look at the output that produces, on line 88 corresponds to the execution of line 3, and we see that 3 space indentation there. And the output line 90 corresponds to executed line 5 in the function. And in that case, the ampersand is indented, but then it's the spaces after the ampersand that become significant for that. So there's only one space after the ampersand before it says less. And so we get less indentation there, as we see on the output line 90. Okay. You can also, as an alternative way, you can span across multiple lines using a double chevron string. So if you use two chevrons at the beginning and end of the string, you don't need to use the ampersands, and you can span any number of lines from the beginning to the end, and as long as you have a closing pair of chevrons at the end, that will be a multi-line thing. So you can see what happens there, and the same rules for indentation apply as applied to the string, except you don't have to use the ampersand at the end of the line. You can use an ampersand at the beginning of a continuation line, like you see on line 2 there, that allows us to explicitly denote indentation of the string. We can say where the ignored lines stop, and where we actually continue with the lines. And then, but you can, we're not restricted in a double chevron string. You can use the ampersand at the end of a line. It's accepted, so it doesn't penalize you for using, but you don't need to use that. I did skip over a point here, I think. The second point on this slide was that you can use the double chevron to span multiple lines without having to use the ampersand continuation character, but there's a little bit of a penalty. It's a plus and a minus. When you use the double chevron string, we ignore any backslashes in the string, so there are no escape characters. So if you wanted to type a string like a file name that contains backslash characters between folder names and so forth, you could do that using a double chevron string, and then those backslashes will be just regular characters. So in other words, if I'm up here and I type this, and I type C:\\ABC DEF like this, it doesn't like that, because those look like those should have been escaped characters. But if instead I use a double quoted like this, then those characters are ignored as escape characters, and they just become regular characters in the string. So that makes it easy if you've got file paths that you're coding hard-coded in, or part of the path is hard-coded in. You can do it like this, which is analogous to what you would obviously be able to do with regular strings like this, because we don't recognize escape characters in regular quoted strings. And let's see. And so that is actually, I think, the last slide. So we are, boy, I've only left myself 5 minutes in the hour, but any questions that you may have?